Hi guys, so today is a short lecture, but several important things I need to let you know. So first, we're going to have a quiz on Thursday this week on Vim. It's going to be in the class, not in the lab. And we also have a lab, which is, let me see if there's anything difficult there. Oh, very simple FPGA basics. The students in 241 Logic 1, they already, did most part of it. Just try to refresh your memory, just do it again, right? Reinforce it. Very simple experiments. And okay, let's take a look at the two things I want to talk about. First, blocking and non-blocking assignment. If you scroll down, that's the first tutorial of the class, not the lab, the class tutorial. Okay, and if you scroll down to here, you can see that there are two different types of assignment in Verilog. And if you have this symbol, there's no space in the middle. Okay, this is a non-blocking assignment, and the other one is blocking assignment. But just looking at the name, it's not making too much sense. So what does that mean? Let me give you an example here. So the first three lines of the assignment, these are blocking and non-blocking by looking at here. It's a blocking assignment. So what does that mean? What does blocking mean here? That's the only part. Keep in mind, Verilog is very simple language. It's very similar to C or C++ or MATLAB. It's very simple. And this is pretty much the only part that confuses people a lot. Okay, don't get scared by it. It's very simple. And the first one is a blocking assignment, and why is called blocking? That's right. That's right. Yeah. So whenever it's doing assignment here, it's blocking the next one or preventing the next one from being executed. So which means after all the three lines are being executed or done, what is the data in Y1, Y2, and Y0? X in everywhere. Okay. What about the other one? There's a non-blocking assignment. How do we understand it? Yeah, it's like a parallel in, parallel out register, shift register. You give a clock to the three of them. The data is getting through the three flip-flops at the same time. It's just like, okay, so it's not waiting for any changes, actually. So after the assignment, X is going to be Y3, but the previous value, the previous value of Y3, but not the current value, which is X, right? It's going to be the previous one will be assigned to Y4, and the previous Y4 will be assigned to Y5. Just keep in mind. That's the only difference. And the convention in Verilog is when you have combinational logic, which is just a static logic gates, static logic gates, you use these blocking assignment. But when you do a sequential logic, you do a non-blocking. It's just a convention. And if you look at the behavioral assignment, this is most popular one actually because when we apply everything on the FPGA board, it has a 100 megahertz clock. It's actually very fast. So whenever it's always rising edge, it's a pause edge, which is the rising edge of the clock. It's going to do all the updates. It's going to update all the data in the block. So this is called a behavioral test. So I want to, since you have taken logic, right? So why a lot of times we want to use clock to control it instead of using just combinational logic? Why not just using combinational logic instead of like adding a clock to it and making it more complicated? And so you can see this is how you can use a clock in your Verilog code. And after you implement it into the FPGA board, it's going to use that clock on the board, which is the 100 megahertz, pretty fast, to update all the logic in your circuit. So why do we have to use a clock? In digital circuits, right? Memory. Yeah, partially correct. And remember, you did all the state machines. It has all the states for sequential logic. It's actually in the real world, in the real world applications, they do need the states to be updated. So you have the same digital circuits. You cannot, get an engineer here just I need another state, just update it for me right now, right? Tape out another circuit for me or reprogram it. It's not really realistic. It's just the digital circuits with different states, and how to update all the states. You have to have some, trigger or stimuli to make it happen, and that stimuli is literally the clock. So the clock is going to update the digital circuits to make it into different states. They can run the sequential circuits. And in the future, you will run so many different kinds of sequential circuits, like all the communication protocols you have learned, or you will learn in microcontrollers, these standard communication protocols. You do need a clock to, synchronize all the behaviors at the same time. You want to send the data to it. You want to use a clock to synchronize everything and update the state as well. So just keep in mind, it's important, and we do need a clock to design digital circuits. That's why in Verilog, you can see this is how we put a clock in the circuit. So whenever, always at a rising edge of the clock. Okay. Then do this. If you have only one liner there, you don't need a beginning end. If you have multiple lines, you have to use a beginning and end to wrap it up, right? So it's being included in the one always block. Okay, so for this example, you can see that initially I gave y, which is a. You can see this is how we form that data type. It has like an array in C++. You can see it has how many elements in there. What's the length of it? 0 to 5, right? But usually it's being written as 5 to 0. It's MSB to LSB. Okay, MSB to LSB. So 5 to 0. From left to right, it's 5, 4, 3, 2, 1, 0. So how many bits in that register? 6, right? It's like 6 register type. It's like 6 different flops in parallel. It's a register type. It's a reg type data. It's able to store data like a flip-flop instead of just a wire. Whenever you have to assign some initial value to this variable, like for example, here is this example, I have initial y and I assign this, it's a 6-bit binary data, right? All zeros. I assigned this binary data to y, so y has to be able to hold it. You couldn't let a wire to hold it. A wire, just a wire. It's a volatile, but a register is not. It can memorize the data. So because I have to assign the initial value to it, so in this case, I have to use a register type for y. Make sense? Okay. And in that case, I got a y as an initial value, which is all zeros. And what is x? Do I have x for it? No, this is probably not the whole example. I probably need a test bench for it. Okay, anyway, so you may need a test bench to apply the clock and x. I don't have the clock as well, right, as the input. It just has an initial value for y. But I need a test bench to assign a clock or x to it. And then you can do the testing. And you can see the difference between blocking and non-blocking assignment. Yeah, just read through it, see what are the options to test this code and find out what are the differences between non-blocking and blocking assignment. And another example I want to talk about is this one. Okay. So here's a timing diagram I drew by hand in Visio. I just drew it on the computer. And I think there's one task that I ask you guys to hand draw the timing diagram first and then run the simulation to verify it. See if you can, analyze it in the correct way. Let's look at the code first. I don't want to run it too fast. I think the first, here's the module. Okay, it's a combinational logic, but has a time delay here. I don't think this is synthesizable, which means you can run this kind of example in simulation on Vivado, but when you have a time delay like that, you will not be able to implement it on IPGA. So, which means you cannot synthesize it to a certain thing physically inside the chip. So this is just for simulation purposes, just to let you know. So not all the RTL, it's register transistor level, so RTL, which is actually Verilog. So not all the Verilog code is synthesizable. For example, this one is not. Okay, this one's not synthesizable, and it's a very simple combinational logic. You can see it has 2 inputs, 2 outputs, and output 1 is formed by this combinational logic, and the AND logic has a higher priority, same as OR. So this one I didn't put a parenthesis here, but you should know that the AND logic and the OR logic are being executed at the same time, and then the result is being XORed to get out 1. Okay, this is very simple, just an inverter. Okay, inverter. So output 2 is just nothing but inverted results of the second input, and it has to be delayed by 20 nanoseconds. This is inside the module. This is a module that has a logic inside, is in the box. But I need a test bench. If you look at the test bench, it's more confusing. The test bench here, it take test 1, which is the module that we're looking at, right? This one, which has a 20 nanosecond delay in there. Okay, so it instantiated. Sorry, I can't get a wrong word last time. So instantiated here as test 1 as a unit under test, and make all the connections. So again, the port right after the dot is a port from where? From the unit under test or from the port of the test bench? No, the first one.
Oh, the first one?
Yeah.
From the module that
Yeah.
test bench, the other one.
Yeah. But you can tell here, right? Because this is as out 1T, right? Out 1T. So you'll know that the one after the dot is the one from the unit under test, right? That's how you make the connections. And so this one is already included in the test bench. I already formed a test bench. What's the name of the test bench? As the outer layer of the test, right? It's like I grab, so the test bench, you can imagine, it's just the breadboard in the Circuit 1 lab. You grab a breadboard, and that's actually the test bench. And you put your chip, so the chip is the unit under test. That I made a test, made this module here is called test 1, which is a little chip you can grab from the drawer. It has all the ports, right? But it doesn't have any signal on it before I connect anything. So this is the same thing. So this one is just a chip. The module is just a chip. Has 4 pins on the chip, and I grab it and put on the breadboard, which is the test bench. But the breadboard itself is not a test bench. I still need the signal source and probes from the benchtop equipment to form the entire test bench system. But now you can just imagine that the test module is just a chip that I placed on the breadboard in the circuit lab. And see, I plugged it into the breadboard and make the connections, right? And then I'm going to connect all the signal lines, which is the signal, the power, or the function generator, the probe to the oscilloscope on the from the test bench equipment. These are all these testing equipment to give a stimuli to the circuit and probe the results. So that's the test bench. Okay. So here's the chip I plugged it in, and here's the test bench. And I have to use initial, begin, and end, right? If I have multiple lines, I have to use begin and end to wrap it up. and there's no difference as a module for the test bench compared to the chip module. Could you tell any syntax differences, or the test bench is a different Verilog module or not? It's mostly the same. It's just a module with ports and N module.
Do you need the time scale on the unit test?
I do have to do it because of the simulation file, but because you can see I have a 20 here, so I have to specify that as, if I don't have this one, I don't need it. So that's why this guy is not synthesizable. It's just a simulation file.
Okay.
Right. Then let's look at the test bench. Okay. Okay. And did I assign initial values to the two inputs? Yes, they are zeros. So they have to hold the value, right? So they must be wire or rag. Are they rag? Okay. What about the output? That's all right. I just need to probe it, right? So they are just wires. And then right after the initial assignment, I directly apply 100 watt, 100 nanosecond time delay. And after that, I start repeating. It's like a loop for 4 times. So no matter what, you just have to give 100 nanosecond delay. So when you draw these timing diagram, right? See, you just have to do it from 100 nanosecond. It should be 0, right?
Yeah.
Let's see. So for example, it's not 0, it's 100. Let's assume this is correct, right? And then it starts at 100 nanoseconds. So I got 100 nanosecond delay already, starting from here. And then I'm reaching here right now. So I have to do another 100 nanosecond delay first. I have to do another 100 nanosecond delay here to 200 nanosecond, and then start changing the value. So here is a change to the data inputs. So for the first 200 nanoseconds, in 1 and in 2 should be zeros, right? For the first 200 nanoseconds. So these are zeros. For L1, if you look at logic here, 0 and 0 is still 0. 0 or 0 is still 0. And then you XOR 0 is still 0. Okay, so L1 should be 0 for the first 200 nanoseconds. So 200 nanoseconds should be zeros for L1. And what about L2? Inverse of in2, right? It has to be delayed for 20 nanoseconds. So during the first 20 nanoseconds, it actually didn't do anything. It should be, a red line. Should be nothing unknown, right? And it should be 1, right? So that's why it's delayed for 20 nanoseconds and shows a 1 here for the first 200 nanoseconds, and then it starts changing. So changes starts from here, and this is the 2 bits and being added to a 1 bit binary number, which is 1. It's just like you combine the 2 bits to form a 2-bit binary number, like 0, 0, right? 0, 0 plus 1, which is 0, 1. So in 1, in 2 as a 2-bit binary number becomes 0, 1 after 200 nanoseconds.
What is the 1?
So just 1 bit. 1 bit. Okay. 1 bit binary number, which is 1. And you see it should, after the 200 nanoseconds, it should be 0, 1, right? But it's not. So I should change the label here. It should be 0, 100, 200. Got it? Okay, but anyway, so we assume this is 200 nanoseconds. So it becomes 0, 1, right? Becomes 0, 1. And let's go back here. 0 and 1 is, okay. 0 or 1 is, okay. 0 extra 1 is, okay. So out 1 should be, right? What about out 2? The trickier one. What about out 2? Yeah, out 2 becomes 0, but has to be delayed for 20 nanoseconds. So that's why it's delayed for 20 nanoseconds and becomes 0. Okay, that's how you do the analysis. And just keep going, keep doing that for all the 4 loops, and enjoy it and verify it using simulation. Okay? So see, here's 0 nanoseconds, right? So the first, this one start from 0 to 200 nanoseconds and then get into 0 after 20 nanoseconds. So that's why this is wrong. This should be 200 here for all 2, right? Okay. I think that's the only 2 things that I didn't talk about last time, but all the rest of them should be straightforward, I think. So I give you the time to you guys instead of keep talking, which will be useless. You have to put your hands on the keyboard and start typing, right? So you can practice. You can start working on the lab, the first tutorial to do the report, write the report, and also practice on them. You can ask questions whenever you have any, right?
So for the lab, when you said you want to do all the commands, you want to literally do every single command.
No, not all of them. I think I listed the main ones as the bottom, the tutorial one, lecture one. Okay. Yeah. I recorded, so it's okay. All right.